You know, the Linux kernel, it's the engine behind pretty much our entire digital world, powering everything from our Android phones all the way up to the cloud. But deep inside that engine, there's this hidden cryptographic core, a super complex set of locks and keys that keeps everything safe and secure. So today we're going to pull back the curtain and see how it really works.
And look, this isn't some, academic question. This affects your laptop, your phone, the servers that literally run the internet. But when you start to dig in and look for what's actually doing the protecting, you run into this puzzle.
On one hand, you've got the Linux Crypto API, which is like this huge, vast library just packed with hundreds of different algorithms. And some of them have these incredible names, right? Anubis, Kazad, Twofish. But in reality, all of our security pretty much relies on just a handful of champions, like AES and SHA-2. So what's the deal? Why have this massive arsenal if only a tiny fraction of it ever actually sees any action? Let's find out.
Okay, so to get to the bottom of this, we've got to look at the three main places, the three battlegrounds where the kernel puts cryptography to work. All right, first up, data in motion. We'll start there. Anytime you fire up a VPN or you see that little lock icon in your browser, yep, the Linux kernel is right there, working in the background, making sure your traffic is safe.
And the secret sauce for all this is the kernel's crypto API. Its real advantage is performance. See, it keeps all the heavy lifting for encryption inside the kernel, so it doesn't have to waste time handing data off to other applications in what we call user space. That speed is absolutely crucial for protocols like IPsec and TLS. But this whole approach, it actually sparked a huge debate, a real philosophical showdown in how we should build secure systems.
So in one corner, you have IPsec. It's all about something called crypto agility. Basically, it gives you this enormous menu of options that two systems can negotiate between themselves. And in the other corner, you've got WireGuard. It's a much more modern VPN, and its philosophy is the total opposite. It's super opinionated. It just tosses that huge, complicated menu in the trash and says, nope, here's the one, single, super strong way we're going to do this, period. And here it is. This is it. WireGuard's entire cryptographic toolkit, right here on one simple slide. It uses this fixed set of modern, really high-performance primitives for everything from key exchange to encryption. And the result of this incredible simplicity, it's just mind-blowing. The whole thing is less than 4,000 lines of code. Think about that. That makes it tiny, ridiculously fast, and way, way easier to check for security bugs than its old, complicated predecessor. Okay, so securing data while it's zipping across a network is one piece of the puzzle. But what about protecting it when it's just, sitting there on your hard drive? Well, that brings us to our second big pillar, locking down your data at rest. Now, tools like dmcrypt, technically, they let you pick from a bunch of different ciphers. But let's be real. In the wild, when you're talking about encrypting your entire disk, there's really only one choice, one algorithm that just rules them all.
And that king is AES, the Advanced Encryption Standard. It's the default, it's what everyone recommends, it's just the overwhelming choice for disk encryption in the Linux world. But why? There are other secure options out there, so what gives AES its crown?
The reason for AES's total dominance comes down to one word: speed. Raw, blistering speed. Just look at this chart. We're not talking about a small difference here. The gap is absolutely massive. And why? Because pretty much every modern CPU you can buy has special hardware, dedicated instructions called AES-NI, built specifically to run this one algorithm and nothing else. This makes AES just orders of magnitude faster than any alternative that has to run in software. The end result is you can encrypt your entire disk and you'll barely even notice it's happening. But, having a fast algorithm is only half the battle. You have to use it the right way. And for disks, that means using a special mode called XTS. Just think about it for a second. The data on your disk, it stays in the same physical spot, right? It doesn't move. So XTS is this special mode that's designed to stop attackers from finding patterns in data that gets encrypted in the exact same place over and over again. Super important.
Okay, so we've protected our data when it's flying across the network, and we've locked it down when it's sitting on our disk. But What if the operating system itself gets compromised? What if you can't trust the code you're running? And that brings us to our third and final pillar, making sure we can trust the code.
You see, the kernel isn't this one giant monolithic thing. It's modular. That means it can load extra pieces of code, we call them modules, for new hardware or new features. Now, to stop a bad guy from sneaking a malicious module in, the kernel checks its digital signature first. It's usually done with RSA or ECDSA. And that signature is basically a guarantee that the code is legit and hasn't been messed with. But here's the catch. That signature is only as strong as the hash algorithm it's based on. And that's where the story gets really interesting.
For years and years, the go-to hash algorithm was SHA-1. Everybody used it, it was considered secure. But then, in 2017, everything changed. Researchers pulled off what they called the shattered attack, and they proved, practically, that SHA-1 was broken. Its reputation was, well, shattered. And the Linux community, to their credit, didn't wait around. They immediately started migrating away from it. So today, the kernel defaults to the much stronger SHA-512. And this whole episode just proves that security in Linux isn't some static thing. It's a living, breathing system that's constantly adapting to new threats.
So as we've seen, a pretty clear pattern has emerged, right? A few incredibly powerful algorithms have really come out on top. And now we can finally go back to that first question we asked. Why this tiny handful of winners? We can finally reveal the forces that are really at play here, the ones shaping Linux security.
It really all boils down to three powerful forces. First up, speed. It's just undeniable. Hardware acceleration, like AES-NI, creates this insane performance gap that makes AES the undisputed king of disk encryption. There's just no contest. Second, trust. You've got industry standards like FIPS 140 that basically create a short, pre-approved list of algorithms that everyone knows have been tested and vetted, so they can be trusted. And finally, evolution. The community itself acts like this vigilant immune system, right? It's always on the lookout, actively finding and phasing out weak algorithms like SHA, the moment new research shows they're vulnerable. So these three forces, speed, trust, and evolution, that's it. That's why we have these few champions dominating the field.
This whole ecosystem, this dance between speed, trust, and evolution, it's what built the incredibly secure kernel we all depend on today. But the next big challenge, it's already on the horizon. I'm talking about quantum computers. Computers with enough power to potentially break many of these champions we just talked about. So the question now is, how long will today's winners really rule? And who, or what, will be the next cryptographic heroes? But hey, that's a story for another explainer.